Hello, all. Welcome. This is our first foray into online physics classes. So, hopefully, this goes well. Um, Being new to this, I'm sure there are a lot of things that I can do to improve. So, if you think of something that would make this experience a lot better, let me know, and I'll see what I can do. Um, as we discussed in class, the plan is for me to go through a lot of the derivations and key concepts in these videos, and then to make the more normal class periods more homework help slash problem solving sorts of times, and also lab periods. So anyway, the first topic that we will cover is kind of a synthesis um, of things that we've learned before with new ideas. So, way back, we talked about uniform circular motion, or even just circular motion, and we had centripetal acceleration. And then more recently, we have had Newton's three laws. So, the first law was the law of inertia, which stated that if there was no net force acting on an object, it just continued to travel with a constant velocity if it initially was moving. And if it was at rest, it stays at rest, which I suppose is also a constant velocity. But and so that was the first law. And then the second law told us that the net force on an object determined its acceleration through the formula F net equals mass times acceleration. So in today's class, um, we're going to use the second law quite frequently. And we're going to combine the second law with our knowledge of circular motion, namely the formula for centripetal acceleration. And we'll have varying levels of problems. They'll start very simple, and then everything will be nice and flat, and maybe just one or two forces, and then we will put things on it at an angle, and then we will incorporate friction, and then we will incorporate both angles and friction. And after we do all those examples, you can pretty much handle anything. The basic method, though, the basic strategy in all cases is always the same. Step one, draw the free body diagram that's relevant. And when doing that, you need to put all the forces that act on that same object. And having drawn the free body diagram, we want to choose coordinates such that if we can, such that the acceleration is simple. And that by simple, I mean it will point in one direction alone. In physics 1, we can usually do that. In dynamics, that may not be possible. And then you're stuck with a hard problem. And after we choose our coordinate system, then we want to decompose the forces in our free body diagram in terms of that coordinate system. Having done that, it's really just clean up bookkeeping. So we want to express the net force in X and Y and set those equal to the mass times acceleration, and the rest is just algebra from there. So I thought I would kind of remind you of some of the key formulas for centripetal acceleration, and then we would start in on some examples. So the key formula for centripetal acceleration is going to be the following. I have to learn how to space myself here. So we know that for centripetal acceleration, which is relevant when we have motion around a circle. So you can imagine there's a circle of radius r. And if we have a point on the rim of that circle spinning around with a velocity v, or actually I should say, you could say tangential velocity, or maybe at this point I should just say speed. But anyways, it's usually people write v or v tangent, so I'll do that so it's really clear. Then what we found before was that there was, because the velocity was continuously changing, there was always an acceleration. We learned that the acceleration points towards the center of the circle. And not surprisingly, the velocity vector, oh, that was not very good, would be tangent to the circle, as like that. Okay, so this is what we found before. And what I want to do today is to combine this kind of information and along with the formula that we found, namely that the acceleration had a magnitude, and this would be the radial acceleration or centripetal acceleration, and it had a formula given by v tangent squared divided by r. And that's true whenever you have circular motion. And I know I wrote actually that it was uniform circular motion, but in fact, this formula would still give you the radial component of acceleration, even if it was non-uniform. So if you had a torque and the object was speeding up and slowing down, you would still apply this formula to find the radial component of the acceleration. We'll deal with the tangential acceleration later when we get to torques. Okay, so our task for today is to combine this formula with our knowledge of Newton's laws and to see how they play out. Together. So many students struggle with circular motion problems because the motion isn't linear anymore. It's round and it's a little bit more complicated visually. But mathematically, when I was a student, I always felt that, in fact, circular motion problems are easier than any other kind of problem, simply because if I knew that it was circular, then I knew already from the start the formula for the acceleration. It'll be that centripetal acceleration formula. And you just know that that's going to work into the problem somehow. So when you have uniform circular motion or just circular motion, you actually have more information than you often do for other problems rather than less. So depending on how you think about it, that should help you rather than hurt you. The downside is it is a little bit tricky to visualize things. Okay, so I was thinking about what kind of example we could use to get going. And I thought we would use the very realistic example of a cowboy in space. So a cowboy in space has a lasso, and for whatever reason, he's tied his toolbox to the end of it, and he's swinging it around his head. Okay, so you've got a cowboy in space. Let's draw a picture so you can kind of see this. So here's my cowboy in space, and he's swinging a lasso up over his head. He'll have really long arms for me. And he's going to swing the lasso, and it's got the toolbox on the end. Okay? And I'm going to go ahead and assume that the lasso has some length, let's call it L, from his hand. I'll give you numbers here in a minute. But I'm going to want you to solve this problem symbolically and then plug in when we're done. Okay, so he's swinging this lasso around his head, like so. Now, why did I put the cowboy in space? I put the cowboy in space so that it was realistic to have a circle that was just as the toolbox goes around in a circle, the rope lies in the same plane. So this is kind of the simplest starting point, and then later examples will be more complicated. Okay, so let's just for now, let's I guess I'll go ahead and give some numbers here. So let's see. Let's imagine that the mass is 10 kilograms, and let's imagine that the length of the rope was 3 meters, and furthermore, let's take it as a given that the toolbox is going to spin with a speed of, I don't know, 24 meters per second. So we could say V equals 24 meters per second. Okay, so we are going to try to analyze this problem, the cowboy in space, emphasis on space. We're going to need that fact. And we're going to use these as givens. And the goal is to find the tension on the rope. Okay, so we want to find the tension on the rope. Now, this is a force problem. So we handle it the way we do all force problems. Step one, we draw a free body diagram. And since I want to find the tension, I need a free body diagram with the tension in it. And the natural object to focus on is the mass. So we're going to draw the free body diagram for the mass as it's going around. Okay, so let's think. What are the forces that act on the mass? Well, here's my mass. I have a tension force, and we're already a little bit, we have a choice. Because yes, I drew the rope like this, but you have to remember it's going around in a circle. And with a little bit of forethought, you can minimize the number of minuses. So the way I drew it, the rope is actually pulling the mass in the negative direction, which is fine. But then I have a minus sign floating around that it has to cancel. Or I could wait half a cycle, in which case the rope is now oriented around the backside, and then I'm going to get a tension to the right, and it'll be positive. Well, that's probably going to help me not screw up the minus sign. So let's do that. Okay, so right now we're imagining a situation where we've waited and the mass is over on the behind the cowboy's head, and the tension is going to be to the right. Okay, and think for a second, are there any other forces? Well, the cowboy's in space, so there's no weight that we have to deal with. So that's it. Okay, so immediately I can say F net equals the tension. And that's it. And if you want, you can say in the x direction, but it's the only direction that's significant, that's relevant in the problem. So just, you don't have to do that. Okay, F net equals tension. Next, when solving a force problem, after using the free body diagram to determine the net force, we simply set that equal to the mass times acceleration. So we learn that the tension should equal the mass times acceleration. Ordinarily, we wouldn't have enough information to deduce the tension because normally we don't know the acceleration. However, because this is a circular motion problem, I know a formula for the radial acceleration. It's the centripetal acceleration formula. So I can immediately write the tension equals mass times v squared divided by the radius. But for this mass, the radius is simply L. mv squared over r, which becomes mv squared over L. And that's our formula for the mass times acceleration. Because the right-hand side mass times acceleration, and we're talking about centripetal acceleration, because this has units of force, sometimes, and I try not to use this word too much, this is called the centripetal force. Notice, strong, big sirens and red flashing lights. The centripetal force is the name given to MA, or the net force in a circular motion problem. It isn't actually a force that should be included in the free body diagram. It's not a real force. It's really the name we give to the net force for circular motion problems. It's not something that should be added to the free body diagrams. If you add it to the free body diagrams, then you're really double counting all of the forces, and you don't want to do that. So this is just, centripetal force is not a real force. It's the name given to the net force for circular motion. I usually try to not say that. I just say mass times acceleration and stick to centripetal acceleration, because I think students are less likely to be led astray in that situation. Okay, well, now we're ready to compute some numbers. I have a formula for the tension. It's related to the mass times the speed squared divided by L. And I have numbers for all those quantities, so I simply plug them in. And I get 10 kilograms times 24 meters per second, quantity squared, divided by L, which is 3 meters. And I know in class, I prefer to have you guys calculate things, partly because it slows me down and lets me kind of monitor how you guys are doing and who's tracking the details. So when I'm doing these online things, I will just crank out the numbers. If you need to, you should pause the video, run through the numbers before we continue. Don't just plow through and just follow along. Just like in normal situations, it works better if you are actively doing this with me. So I've got 10 times 24 squared divided by 3 gives me 1920. And because we were civilized and we use metric units throughout, we're guaranteed that this will come out in newtons. Or if you don't like that, you can see that it's going to be kilogram, 1 power of meters in the numerator after canceling the denominator, kilogram meters per second squared, which is in Newton. Okay? 1920 newtons. I think we'll take a break here for a minute, and that'll give you a chance to run through this and make sure you get the same answer. And then I'm going to add a wrinkle in the next video. We're going to bring the astronaut back to Earth and solve a similar problem. If I can stop the video.